So I'm going to tell you about the spectroscopic Hamiltonian diatomic molecules. Okay, we call that the effective Hamiltonian. It's a matrix, it's a fit model. It represents everything that you can observe for a diatomic molecule. It is not the exact Hamiltonian. A quantum chemist would not calculate that. They could derive it if they chose to from what they can calculate, but it's different in several important ways. Okay, fundamental to the effective Hamiltonian is a separation of variables to nuclear variables and electronic variables. That's called the Bornoppenheimer approximation. So we have electronic, vibrational, and rotational degrees of freedom. These are nuclear. This is electronic. Function. Just go. And now we're all out. Okay. And so the Bornoppenheimer approximation allows us to make this separation. Nothing really allows us to make this separation, but we do it. What is this separation good for? Well, it enables us to approach the problem of a many electron molecule without having to deal with all of the degrees of freedom that would be associated with many electrons plus several nuclei. It enables us to think about things called electronic states and rotation vibration levels of electronic states. And that's an enormous simplification. Now, a lot is slipped under the rug. These things that are slipped under the rug are going to be critical to understanding dynamics. But first you need to have a picture of what would the molecules behave like if they were really simple, if nature had been more kind. But then there'd be no dynamics, there'd be no life, it would not be such a good thing. Welcome. So we're going to create a world which we understand, which is free of all these difficult terms, and then we're going to bring these difficult terms in. Use this simple picture that we started with in order to be able to calculate all of the complexities that we had suppressed when we defined the simple world. Okay, why diatomic molecules? Well, they're not atoms. And chemists are generally interested in molecules. This is the simplest thing that has all of the complexity of chemistry. Diatomic molecules are also special because of several things. You can go from a spectrum to the effective Hamiltonian. And there is an exact inversion. This is not true for any other kind of molecule. So one can approach the problem of diatomic molecules without having to make any assumptions of models. One can then take that approach and a lot of the approximations that work and use them for more complicated systems. with confidence that you know the limits of these assumptions and approaches and models. You can also have a complete sample of all relevant states. Now, you're not going to look at all states of the molecule, but with a diatomic molecule, you can essentially measure everything that is relevant to whatever question you want to ask. Because the vibrational density of states and the electronic density of states increases very, very slowly. And so one can resolve all of the stuff that you need to create your model and to answer your questions. And this is not generally true for polyatomic molecules. In fact, it's almost never true. So we need somehow to develop ways of extrapolating into polyatomic molecules to deal with this rapid increase of density of states and complexity. And we use diatomic pictures as a way of doing that. Okay, I said there's an effective Hamiltonian, which is our model for representing everything in a diatomic molecule. And how is it different from the exact Hamiltonian? Well, you might start with the exact Hamiltonian. And you would partition the exact Hamiltonian into a zero-order picture plus everything else. Okay, this zero-order picture is based on models that you understand and can calculate with. This is the simple world. It might be rigid rotor, harmonic oscillator, hydrogen atom, particle in a box. The particle in a box is a good representation for valence electronic states. The hydrogen atom is a good representation for Rydberg electronic states. The vibration of the harmonic oscillator is a good representation for vibration, rigid rotor for rotation. And so we might put in things for which we have exact solutions, and we know how they work. And we have eigenfunctions of this, which we can use to evaluate matrix elements of whatever is inconvenient. Now, there's a lot of stuff that I'm hiding here, but that's the formal approach. And this is an extremely good time to ask questions. So this enables us to define a complete basis set. In other words, we have a complete set of wave functions, or Bras and Kets, that enables us to evaluate the effects of the terms that we've decided to exclude from H0. We can choose which terms we put in H0, depending on which interactions we think are important and ought to be dealt with in the zero-order model, and which ones are only small perturbations that we won't have to, we will have to deal with, but will not be necessary for being able to recognize in either the ab initio calculations or your spectrum complexities. And we'll see how that works. Okay, so we divide the Hamiltonian into a zero-order part and everything else. Then we have essentially an infinite matrix, which is no use. And we have to approximately block diagonal IZ. And that's called the Van Vleck, or contact transformation. And this is basically second-order perturbation theory. It's a procedure which is describable exactly. And it enables us to take this infinite matrix, which is the exact Hamiltonian, and cut it down to small pieces, blocks that we can diagonalize. And we think of that as our fit model, as the effective Hamiltonian. This is an essential part about which I will talk very little. But it is the difference between what a quantum chemist would calculate and what a spectroscopist would manipulate. So, and that gives us the effective Hamiltonian, which is a matrix that has a bunch of blocks along the diagonal and some small stuff off the diagonal that we're allowed to neglect, except whenever there occurs accidental degeneracies. It's possible that we have a bunch of states associated with this block, and they have their own energies, and a bunch of states associated with this block. And there's a tiny term here that couples states in these two blocks. And normally, the energies are very different. The difference in zero-order energies, or block energies, are large compared to the coupling term. And so we can ignore them. And we do. But when, by accident, the levels get close together, we can't. And we have to do something special. And that's called dynamics. It's called a perturbation. It's called the interesting stuff. It's the stuff that most textbooks slip under the rug. So we have a procedure for simplifying the exact Hamiltonian. And there's complicated dynamics because these blocks also have off-diagonal elements. But those are sort of part of our zero-order model. And then there are these exceptional things which lead to unexpected and useful energy flow between different parts of a system that are normally not in communication. Yes?
I had two questions. So is the Van Vleck transformation, the purpose is to minimize those off-diagonal elements between the blocks?
Exactly.
Is that the goal?
Exactly.
Is it designed such that it's an optimization routine to minimize that, or is it a set routine which does that, which is known to do that?
It's a set routine. It's so the procedure is to add terms on the diagonal and off the diagonal in each of these blocks that compensate for these out-of-block terms. And so so let's call this the N, and this the M block. Okay, so we have a matrix element between one member of the N block and one member of I, and one member of the N block. Okay, so that's an off-diagonal matrix element. It's an out-of-block matrix element. Okay, and so second-order perturbation theory would say, well, we can correct the energies I'm missing something. No, okay. Okay, so we have an off-diagonal matrix element between the ith element of the N block and the jth element of the N block. And so then we come back via from the same place, but to a different member of the N block. So this is going to be a correction to the Ni and K element of the N block. So that's an off-diagonal or diagonal element of that one block. And so then we have E and I plus E and K over 2 minus E and J. So this is second order perturbation theory. It's a matrix element squared. And this is an energy denominator. And we're taking an average of these two guys that are near each other. And now this remote one. And that's the correction that you automatically calculate to the elements in these various blocks. And you don't have to diagonalize a matrix or anything. It's just you look at what the Hamiltonian tells you, and you automatically make these corrections. And that leads to all sorts of horrible, ugly second-order constants and confusion about what is in the effective Hamiltonian. Because we call the things in the effective Hamiltonian by the same names that the quantum chemists call those elements in the exact Hamiltonian. And so there is always contamination. Dixer called it confusion or mixing of the mechanical and electronic significance of parameters. And he wrote a very beautiful paper in the early 70s where he talked about how you separate these mechanical and electronic meanings of parameters. But mostly spectroscopists don't care about that because you need to fit your spectrum, and what you get when you fit the spectrum is not just energy, a formula that fits the energy levels, but you get quasi-eigenvectors, which enable you to calculate whatever you want. And you do make some small errors, but you have to worry about what was that transformation you did. But it's completely mechanical, and you can undo it in a sense to make a connection between the exact Hamiltonian and the spectroscopic one. You said you had two questions.
Oh, the other one was just practically, how big are those block diagonals? Like if you had like an actual problem you were working on?
It'd be really big. But again, those blocks are more or less self-defining from your zero-order model.
So you try to make it so those block diagonals are as big as the computer can handle?
Unless it's not necessary.
Right, okay.
Yes.
And are those typically, is like each block represent practically like a vibration, and so within the block, you're diagonalizing to get the rotational state? I mean, what is it practically? What do the blocks represent?
Well, have you heard of, say, something like a triplet pi state? A triplet pi state is a collection of 6 independent electronic states that are somehow represented as one state. Okay, so it's a thing, 6 things that belong together, and there's off-diagonal elements, and there's stuff in there. Or suppose you have a triplet pi state and a triplet sigma state that are near each other and that are so close.
Each block is an electronic state.
Each block might be 1 electronic state or 2, or sometimes when there's true complexity, some serious interstate coupling, you have all of the vibrational levels of 2 states in one big block. So it's whatever you need. Whenever the interaction matrix element is large compared to the energy differences, you have to stick it into something that you diagonalize rather than something you use a formula from second order perturbation theory. Okay, so are you okay? Defend yourself. Okay, I mean, I am not determined to finish 15 pages of notes. It makes my life easier if
I only get through 3 or 4 because then I have in the lecture. Are we all set? I mean, try to formulate a question. I know for the people who've only had 561, this is a reach. But I'm trying to talk about the ideas rather than the equations. That's why I didn't want to write this. I had to think about this for a second. Yes?
So from that block diagonal, do you get the basic elements, the basic vibrations and states that you start? Didn't you already wanted to start with ones that you already knew? And how they come out of there?
This thing will reproduce what you would observe in the experiment. Okay, so this effective Hamiltonian, and make sure that I answer your question rather than what I think you're asking. This is a model which is expressed in terms of molecular constants like omega E, spin orbit constant, rotational constant, some perturbation term. It's a bunch of numbers that when you adjust them so that the eigenvalues of this matrix match the energy levels, you say, I've got the optimum values of these parameters. So this is a model expressed in terms of a bunch of adjustable constants that we think have physical significance. And we have a least squares fitting procedure which adjusts these parameters to match the experiment. Or if we have an ab initio calculation, if we calculated the wave functions and we want to calculate the molecular properties, we convert the quantities in the ab initio calculation to these molecular constants. We put them into a matrix and we calculate the energy level. Did that help? Everybody? Okay. All right, so now we're ready to actually start to talk about the critical thing that enables us to do all of this, and that's the Bornoppenheimer approximation. And there's a lot of confusion about the Bornoppenheimer approximation because a lot of people worry about, is this approximation valid or not? We don't care. It's a self-fixing approximation. It's a method for defining a basis set. A set of functions which is complete and which enables us to calculate all of the Born-Oppenheimer breakdown phenomena, all of the stuff that is outside of the Born-Oppenheimer approximation. And in fact, as you'll see in the next few minutes, spectroscopists don't even use the Born-Oppenheimer functions. They use something else called the Diabatic functions. Okay. The Born-Oppenheimer approximation is the basis for separating electronic motions from nuclear motions. And the basic justification for that, which is, I believe, irrelevant, is that electrons move fast relative to nuclei. So because of this, we have the idea of electronic states and potential energy curves or potential energy surfaces. So what is the Born-Oppenheimer approximation? It says clamp the nuclei. So there's no nuclear motion, no nuclear kinetic energy, no rotation, nothing. And solve electronic vertical equation. Okay, so that's a perfectly sensible procedure because what it does is it says we solve the electronic problem and there is no nuclear coupling. There's nothing. No rotation, that causes trouble. No vibration, that causes trouble. And we get a bunch of, so what we do is we calculate, for a diatomic molecule I can draw this, for a polyatomic molecule it's a little harder. But we get a bunch of energy levels and each internuclear distance. So we might have a series of energy levels that look sort of like this. Or we might have a series of energy levels that look like that. And so we say, okay, here is a bound electronic state, here's a repulsive electronic state. And now we're at the beginning. For the bound electronic state, we can solve for the vibrational levels of that problem simply by saying, okay, here's a potential energy curve. Let us use Numerov-Cooley or some numerical integration procedure to calculate the vibrational wave functions, the vibrational eigenstates of this isolated potential. We can find the continuum wave functions again by using the same idea. So you solve a differential equation and you get the nuclear wave functions associated with these electronic wave functions. So now we've allowed the nuclei to vibrate. We've included the nuclear kinetic energy, but only when it operates on the nuclei and not on the electrons. The electronic wave functions are explicit functions of the electron nuclear coordinate, but implicit functions of the internuclear coordinate. So the nuclear kinetic energy, which is basically that operator, that acts on this. It gives, and so we can calculate the first derivative of psi, and that's going to give some constant and some other wave function. So this might be a small constant, but this operator, when operating on the product of the electronic and vibrational wave function, you have the second derivative of this times the vibrational wave function, you have first derivative of this times the first derivative of the vibrational wave function, you can have no derivative of this and the second derivative. So there's a whole bunch of stuff that we're not yet bringing in, and that's slipped under the rug. That's one of the Bornoppenheimer breakdown terms, but we can calculate them. There's nothing mysterious about it. We have, when we solve the Schrodinger equation, electronic Schrodinger equation, we get these curves. We can find the vibrational wave functions of these curves. We can find the rotational wave functions of these curves. So we can let the nuclei start to move, and we know what to do. But we know when we do that, we're cheating. There's something we have to go back and worry about, but we normally don't worry. Okay. We expect potential curves to look like one or the other of these. But sometimes we get a potential curve that looks like this, another one that looks sort of like that. Or sometimes we get potential curves that have two minima and then another one sort of like that. And this is the truth. This is what you get by clamping the nuclei and solving the electronic Schrodinger equation. And these things are called avoided crossings because states of the same symmetry cannot cross. A non-crossing rule. This is bad because these curves have shapes that are offensive to us, to our sense of simplicity. And it's also a warning that the electronic wave function is going to undergo a very dramatic change of electronic character as you go through this. and a slower change of electronic character as you go through that. Well, because why would the curve do that? That's, it can't do that unless the electronic character changes. So we say, well, there must be another kind of approximation that does not allow the electronic wave function to change rapidly with internuclear distance. So these kinds of curves are the Bornoppenheimer or adiabatic curves, and what we want are called diabatic. Now, adiabatic has the sense of moving slowly, and diabatic has the sense of moving fast. And this gets to the last lecture where we talk about Landau-Zener. But the diabatic curves are the curves that would be obtained by allowing these things to extrapolate, and they're the curves that don't change electronic character. Remember, the electronic character changes with R rapidly. Matrix elements of d by dr, electronic matrix elements of d by dr, are going to be huge. And if they're big, then they're going to be large compared to the separations between the zero-order states. And we're going to have to diagonalize a big matrix, which means trouble. It means you either have to know the answer before you start, or you have to do a lot of work in order to get from what you can observe and what you can calculate. Now, what you need to do is clear the diabatic representation when you have this almost singularity or cusp in the wave function, in the potential curve. When that occurs, you know this is the wrong representation. When this occurs, it might be the right representation. Right, wrong is based on convenience, not based on something that gives you a good or bad fit to the energy levels. Either representation, all representations which are complete, give you the same quality of representation of fitting the observed energy levels and calculating all of the dynamical quantities. It's just what they're called is different. And if you chose a physically appropriate model, your labors will be less, and the resemblance between the zero-order model and what you could observe or calculate will be much greater than if you chose an inappropriate model. And this is good for experimentalists because your model, before you include a lot of off-diagonal elements, needs to resemble what you can observe, otherwise you're lost. Okay. The distance of closest approach between these potential curves is twice the coupling matrix element, or twice the electronic coupling matrix element. We know from perturbation theory that as you try to make two levels get degenerate, they can never get closer together than twice the matrix element coupling the zero-order levels. Those of you who don't know that will know it. But so these are the energies as a function of R, and so these curves tell you can't get any closer than this, so that means that there is some electronic coupling term which is half that distance of closest approach. Now, in the adiabatic picture, we diagonalize the electronic Hamiltonian and we ignore the nuclear kinetic energy. The other approach is we're going to diagonalize the nuclear kinetic energy simply by making the electronic wave functions not depend strongly on R. And we're not going to diagonalize the electronic Hamiltonian. This is a simple idea, but it's computationally ill-defined. Because
we know how to collect the nuclei. We know how to say the nuclear kinetic energy terms and the rotation are going to be ignored. The interelectronic repulsion, that's 1 over Rij, or E squared over Rij, sum I not equal to J. It's a lot of terms. And you don't know which one to ignore. There's no way computationally from scratch to suppress a term in the electronic Hamiltonian. So, the Hamiltonian, electronic plus rotation plus spin orbit. These are the important terms in the Hamiltonian, and these are the two terms that we would want to play fast and loose with if we wanted to define a diabatic basis set. Rotation, well, that's just ignored. I'm sorry. So we can turn off the spin orbit, but we can't turn off specific terms in the interelectronic repulsion Hamiltonian. So we have two different adiabatic pictures. Adiabatic relativistic, that's the full smear. That's the Bornoppenheimer. Everything is clamped. We're solving the electronic plus spin orbit. And then we have adiabatic non-relativistic, where we turn this thing off. And so we can, when spin orbit is important, we can diabatize by turning off this term. But there's no way computationally we can diabatize by turning off something in here. Instead, we have to use a simple model. Okay, so let me try to describe what we do. So we start with the adiabatic potential curves. So they might look like this. Okay, and so immediately from these curves, we know 2H electronic 1,2. The coupling matrix element. Then we have to make two approximations. One is that there are only two curves that are interactive. The effects of other curves can be ignored. This is usually a good approximation, but it's not always a good approximation. So, two states only. The other approximation is that the diabatic curves are linear in the crossing region. In other words, we have a diabatic curve and another diabatic curve. Okay. And so what we want to determine is the energy of the crossing, the internuclear distance of the crossing, and the coupling matrix element. Where did
at the crossing. Okay, and there's a couple of pages of what I call non-lecture because I don't want to go through the formulas. At the crossing, these two are equal. And so you get an equation for the value of the crossing radius from these constants. You also have the Diabatic curves, which are what you're given ab initio. You don't have to make any assumptions about the form of these, but at the crossing radius, the difference between these two is a minimum. So the derivative of the difference is 0. And that gives you the value, the R value at which that difference is smallest. That's the crossing radius. The energy difference at this R value is twice the matrix element. The average energy of the crossing value is the energy at the crossing. So basically you have everything you need. So given these things, you can calculate these critical quantities. And now we have a 2x2 matrix, which describes everything that happens involving these two states. Yes?
What exactly is the crossing radius?
It's the internuclear distance. I'm sorry, I should have said the crossing internuclear distance. Okay? So, at some internuclear distance, the diabatic curves cross, and the adiabatic curves have reached their minimum vertical energy separation. And that's what we want to determine. So we want to know RC, EC, and this, and they are all obtainable by exploring the ab initio curves. So then you splice, you say, okay, the diabatic curves just go through that crossing. They're linear at the crossing, and then they sort of join the adiabatic curves, or we can say, all right. So we have a 2x2 matrix. That describes the two-level interaction. So okay, whenever you have a 2x2 problem, it's always useful to separate out. So suppose you have a 2x2 problem, E1, B, B, E2. It's always useful to separate out the average energy. So we have E1 plus E2 over 2, E1 plus E2 over 2, 0, 0, plus E1 minus E2 over 2, V, V, minus E1 minus E2 over 2. Okay, so whenever you're facing a 2x2 problem, it's useful to write it this way, because this, you know, the solutions, they're just V squared plus or minus plus E1 minus E2 or 4. So we have, whenever we have a 2x2 problem, we take out the average energy and we get the symmetric 2x2 matrix. We know the solutions. So
what I wrote on page 6 of the notes is the symmetrized, the average energy in the diabatic representation, and what remains. And so we have P1 minus P2. Remember, I defined the diabatic curves this way. Over 2 R minus RC minus B1 minus B2 over 2 R minus RC BV. This is the matrix that we need to solve. It's a 2x2 matrix. It's diagonalized by unitary transformation. The unitary transformation has the form cosine theta, sine theta, minus sine theta, cosine theta. But this transformation is a function of R, internuclear distance. And so we have the transformation that diagonalizes this matrix, which is an explicit function of R. Now, this theta is a complicated combination of all of the control parameters. So there's some algebra, but basically you know what this is, and so one can write the eigenfunctions of this 2x2 matrix. What are they? Those are the adiabatic states. We can write the eigenfunctions as an explicit linear combination of the diabatic states. We can calculate matrix elements of d by dr, because now we have an explicit function of R. And so all of the necessary matrix elements are now soluble. And so this transformation, which is a model between adiabatic and diabatic, enables us conveniently to calculate all of the off-diagonal matrix elements in terms of parameters that describe either the diabatic or adiabatic potential curves. Things that we can get from either experiment or from ab initio calculation. So it is also very common when you have a two-state interaction. So here is here's diabatic state number 1, and here's diabatic state number 2, and here is the ground state. And if we excite this system with a short pulse, it is very common that the only one of these two states can be excited by an allowed transition from the ground state. And so what one makes is some kind of superposition of the, so we have the diabatic states and we have the, so this is the higher energy eigenstate and the lower energy eigenstate. So, I drew this stupidly. So we have a short pulse, short enough to cover both of these. So we make a superposition of these two eigenstates, which is at t equals 0, purely the basis state that has the allowed transition. And now we've got quantum beats. We have the system going back and forth between these two eigenstates. I'm sorry, we have the system going back and forth between the two zero-order states. So at the time of the excitation, it looks like the allowed zero-order state, and then it moves towards the other disallowed zero-order state. So there's a kind of dynamics. The system is changing its diabatic character with time. Now, we can also record the spectrum in the frequency domain and measure these eigenstates and measure characteristics of their wave functions. And
conclude the same thing about the potential dynamics that you could excite. So, all right. That wasn't what I had planned to say on this. Yes?
So just to sum this up, the only reason that you're working between these two, this adiabatic and diabatic, these two, there's just two limits that try to model reality. And to get the real coupling between these two states, you're just mixing the two different limits.
That's right.
Some clever way that gives you, and that's all you're getting out of it.
Reality
Between the two states.
is neither limit.
Right.
And it's often true that the energy levels that you observe in the spectrum, or that you calculate ab initio by doing everything with the exact Hamiltonian, are closer to one limit or the other. And there's a table on the last page, on the next to last page of what I handed you, where there's a two electronic state interaction in silicon monoxide. And what you see is that the vibrational energy levels calculated from the adiabatic potential curve or from the diabatic potential curve, without considering the interactions between the two potential curves, the adiabatic potential curve, in this case, gives a better representation of the observed vibrational levels, but not perfect. This is the result of an exact fit. So when one includes either the nuclear kinetic energy coupling between the levels of the adiabatic curve or the electronic coupling between levels of the diabatic curves, you get an exact fit of the energy level. And you get the eigenvectors. And you can have the eigenvectors in either representation. So it's not, this table is not saying that neither representation is very good. Both are perfect. But one is closer to reality than the other. And usually you want to use the representation that's closer to reality. In this case, there's only a small advantage to one picture over the other. Usually there is a huge advantage, and one can know in advance whether you want the adiabatic or diabatic by comparing certain quantities, which is not what I want to talk about now. Okay, so now I want to go to electronic vibration rotation wave functions. So we get a potential curve. Somehow it could be adiabatic or diabatic. It's for the ith electronic state. We just count up from the bottom. We can find all of the vibrational levels of this potential curve by doing a numerical integration, by solving the nuclear kinetic energy, the nuclear Schrodinger equation. And so we have the vibrational wave functions, all of them, for all vibrational levels and the continuum associated with this potential curve. So we get the wave functions and we get the energy levels. We can fit the energy levels to what is called the Dunham expansion. These are Dunham constants. Y10 is omega 0, omega E, and Y01 is E. Vibrational frequency, rotational constant, there's lots more. So this is a no insight, no knowledge, empirical representation of the eigenenergies calculated from the potential curve. And these are the things that spectroscopists publish. So one can do a least squares fit to the eigenvalues, or one can do a least squares fit, but one can write V of R, V of psi as sum over I, 0 to whatever, A I psi to the I power. Psi is R minus RE over RE. RE is the equilibrium internuclear distance, and this is a convenient parameter. And that's the Dunham expansion of the potential, and these are a bunch of empirical parameters determined by fitting this to the potential. And there is a Dunham inversion that enables you to calculate these things. Calculate these things from these things. There's lots of ways of going between the potential and the constants, or the constants and the potential, and they mostly involve perturbation theory. Okay, now I slipped something under the rug. Or at least, since I'm not looking at my notes, I'm doing it out of order. We have a effective potential, which is gotten from the clamped nuclei potential, in other words, J equals 0, plus the explicitly known centrifugal correction to the potential. Okay, this is the internuclear distance, this is the reduced mass, this is the rotational angular momentum. So this is the bare potential, no rotation. Now we fix clamped nuclei approximation by allowing the nuclei to rotate. That's one of the terms that we neglected. And that enables us to calculate, to derive the J-dependent effective potential. And the eigenvalues of that then give us E of V and J. Okay, so the ab initio potential curve enables us to calculate all of these things. All of these things allow us to compute the molecular constants by fitting, or by fitting the curve and doing the Dunham inversion, or using perturbation theory. There are lots of connections. But so everything is okay. We've included the rotation. This is the bare nuclei. We call this the rotational constant operator. It becomes a constant when we take the vibrational matrix element of it, vibrational expectation value of it. So if we do this, guy, that becomes B of V. Okay. All right, now we're on page 9. So the Bornoppenheimer approximation enabled us to calculate electronic energy levels for the ith state, but they're normally called T sub E. And it enabled us to get a potential curve. So then, by allowing the molecule to rotate, we have this. And we still haven't included all all of the couplings between electronic states, either the nuclear kinetic energy couplings, or if we've gone to a diabatic representation, the electronic couplings. But this provides the separation that we need between electronic and nuclear motions. And then we can say, all right, are we going to have a model that describes the different parts of the problem, the electronic part of the problem? Are we going to try to explain it as something related to something that we understand well, like the hydrogen atom, or like the particle in a box? And valence states are reasonably well described by orbitals which correspond to different eigenstates of the particle in a box. The energy levels get farther and farther apart as you go up, and as you go up in energy, they have more and more nodes. Or they could be the hydrogen atom for Rydberg states. And so you can sort of have a model for this, and then you can have a model for this. You can say it really wanted to be a harmonic oscillator, but there's some terms that involve cubic and quartic powers of R, or we can make it a Morse oscillator, and we can represent a lot of the molecular constants by using the harmonic oscillator plus anharmonic corrections, or the Morse oscillator. And we get relationships between molecular constants that help us in leveraging our finite number of observations. So we're ready to begin. So in order to really begin, we need to say, well, what did we really leave out? And I'm going to summarize this. For the electronic problem, if we take a diabatic picture, and most spectroscopists are most comfortable in the diabatic representation because it is the one where the electronic wave function doesn't do gymnastics as a function of molecular geometry. So we're more comfortable thinking about the electronic problem in a diabatic picture, and that's no big deal. So, and in that case, this is missing. For adiabatic, D by dr is missing. Vibrational problem. We could use a harmonic oscillator and include powers of R cubed and R4, etc. Or we could use a Morse picture. And so treating cubic and quartic terms, or the power series expansion of the Morse potential in cubic and quartic terms, we can treat them as perturbations. So there's lots of things you can do for the vibration and the rotation. Now, I lied to you before. I said the rotational angular momentum that goes with the centrifugal potential is J squared. It's not. It's the nuclear rotation. It's J minus L minus S squared, which is equal to R squared, where this is now not the internuclear distance, but the quantum, the operator associated with the nuclear rotation. And so we've got some work to do here to correct for the fact that you could have non-zero electron orbital and electron spin angular momentum. So we wanted to use Bj plus 1 because this says the rotational levels are given by a constant times an integer plus 1. But we know j could also be a half integer. But we have a pattern of rotational energy levels. They're given us basically by one constant and some magic expression in the quantum numbers. Well, it's going to be more complicated here, and we're going to discover Wund's cases soon. So the Hamiltonian is written as a sum of the electronic Hamiltonian, the vibrational Hamiltonian, which is really sort of part of this, plus spin orbit, plus rotation. And now I need to tell you about the various terms in each of these operators and classify them according to their type. And so we can know something about the selection rules for non-zero matrix elements. So we want to have a simple way of doing this. And this is the way I do it. For the perturbation term associated with the electronic Hamiltonian, it's okay, this guy is a problem. Well, what is it? Rij is the square root of R1 squared, I squared, plus Rj squared, minus 2 Ri dot Rj. This is a scalar operator with respect to electron I. This is a scalar operator with respect to electron J. This is a vector operator with respect to either electron I or J. This is a dot product of two different vector operators. So this guy destroys all of the one electron quantum numbers. It has matrix elements delta L plus or minus 1 or 0. Lj plus or minus 1 or 0. But this is a vector with respect to many electron angular momentum. So the total J or the total L. This is a vector, dot product of two vectors is a scalar. So this is a scalar operator with respect to all of the many electron angular momentum. So that means delta J equals 0, delta L equals 0, delta S equals 0, delta JZ equals 0, delta LZ equals 0, delta SZ equals 0. And they're independent of omega, which is the eigenvalue of Jz, lambda, which is the eigenvalue of Lz, and sigma. That's the property of a scalar operator. It's diagonal, and it's independent of projection quantum numbers. So this says, well, this thing is only going to operate between electronic states of the same symmetry. Hence the non-crossing rule. Okay. Now for the rotational Hamiltonian. I'm going to have to stop pretty soon, but I got pretty far. The rotational Hamiltonian is B of R times J minus L minus S. becomes B of R times a bunch of stuff. J squared minus JZ squared plus L squared minus LZ squared plus S squared minus SC squared. Those are all of the diagonal elements in Lenz's case A. But we don't know what Lenz's case A is yet. But you see these things and you say, oh, I'm pretty happy. And then we have minus J plus L minus plus J minus L plus. These are raising and lowering operators. Minus J plus S minus plus S J minus S plus plus L plus S minus plus L minus S plus. That's it. So these have matrix elements off diagonal in omega and lambda, off diagonal omega and sigma, off diagonal in lambda and sigma. This is called L uncoupling. This is called spin uncoupling. And this is small, but it's called rotational electronic or spin electronic coupling. So this is what we have to consider. So a basis set of this form enables us to deal with all of the terms here. Now I put L in parentheses. The reason I put L in parentheses is that an atom, a molecule, is not rounded. In order for the orbital angular momentum to be defined, it needs to be rounded. You can think about the effect of the two nuclei on the wave functions around each atom. There's a Stark effect. It causes L to mix, but it preserves the projections of L along this axis. So L is totally wiped out, but its projections are preserved. So,
Isn't that what lambda accounts for, though?
I'm sorry?
Isn't lambda the projection of L on the axis?
Lambda is the projection of L, but because of the cylindrical symmetry, lambda gets preserved,
Right.
but L is destroyed. Okay, when we lose this quantum number, we lose the ability to evaluate these matrix elements explicitly. And these matrix elements, this matrix element explicitly. And we lose the ability to use Clebsch-Gordon coefficients to perform transformations of angular momentum from one coupling case to another. So it's kind of a tragedy, but there are ways around it. The reason it's not such a bad thing is that states with different values of lambda are usually relatively far apart. States with different values of sigma are usually close together. And so we talk about things called multiplet states. Which we denote by 2s plus 1 lambda. And these multiplet states have several values of omega, where omega can go from lambda plus s down to lambda minus s. There's a little bit of complexity here, lambda minus s, in steps of 1. And so, depending on whether lambda is larger or smaller than s, we get a certain number of components to s plus 1. And these states are essentially replications of each other. We don't say for each of the omegas of a state like this, we have a separate potential curve. So we get a bunch of states that belong together. In spectroscopy, there are natural groupings of states, the most common of which is called a multiplet state, like triplet pi, or triplet sigma, or doublet sigma, whatever. The only time the textbook is going to give you what you would like for a rotational levels is for a state which has no spin or orbital angular momentum. Okay. Then J is equal to R, and everything was correct. But whenever you have non-zero lambda or non-zero S or both, you get these multiplet states. And this is a grouping of states that belong together. It's a natural block diagonalization of the Hamiltonian. And the off-diagonal elements within that block are given by this. This is between different electronic states, so that's why we aren't really so harmed by the inability to know L. So, this brings me to the last thing that I'm going to talk briefly about, and that's on the bottom of page 13. There is a very beautiful paper by Nikitin and Zer, which says, okay, we've got several terms in the Hamiltonian. We have the electronic term, we have spin orbit, we have the rotational term. And we're going to choose a zero-order Hamiltonian, which is a good representation of the rotational and fine structure that is different for each of the relative orderings of magnitudes of these terms. So the usual ordering is the electronic is large compared to the spin orbit compared to the rotation. So we have multiplet states. The rotation is small, the spin orbit is big. We have multiplet states, and case A is what happens in this limit. If we make spin orbit small compared to rotation, then we get case B. The rotational pattern forming quantum number is J here. The energy levels are given by B, JJ plus 1. The rotational pattern forming quantum number is N, which is defined as J minus S. The total angular momentum exclusive of spin, and the rotational pattern forming quantum number is N, and the rotational levels are given by this. This is often half integer. This is always integer. They're different. The pattern of energy levels is different. It's nice to know which it's going to be. So if you have three objects, you can order them in 6 different ways. And they correspond to Hund's cases A, B, C, D, and nothing. D, E, and nothing.